All right. Oh, small group today. Today, what's that?
What was that?
Small group.
Oh.
Seems to vary a lot. All right, so today we will continue the discussion of synchronization design. And we started with something relatively simple, like a big fat lock. We went on to this fine-grained locking sort of idea. We'll see some other ways we could do that. If we have time, perhaps we'll get into actual lock design, which is not something everyone needs to get involved with, but it's probably a good idea to know what the alternatives are and how they work. Before we start with that, any questions on the homework? All right, who got started? Okay, so Ben's office hours can be quite useful, and those were yesterday. He does the homeworks first, and so he will have a good idea of how to do it. I usually go through the solutions with him as well, just to make sure that they're good. And so you can usually get good guidance from him. This homework probably isn't all that complicated. I think the one that could be challenging is the last part, the hand-over-hand locking. There's a lot of locks involved, and it's very easy to either not hold the locks that you should be holding, and then end up with an inconsistent data structure, which sometimes will look like an infinite loop. I've run into that. Or maybe even if you try the single-threaded list without any locks, and you do it with updates, then you're going to get an inconsistent data structure. And sometimes it results in a crash. I think I haven't seen a crash, but it certainly could. Sometimes it works just fine, and other times the list ends up looking more like a loop. And so you have threads that get stuck in this loopy list, and it's going around and around because, well, that's what happens when you don't use locks. So in the hand-over-hand locking case, there's a few things that can bite you. One is, oh, you're not holding the right locks, and so you have an inconsistent data structure, and it doesn't work. But it looks like it's hung. And the other way it can hang is you weren't releasing locks, or you're holding the wrong locks one way or another, so that you get a deadlock one way or another. Right? If you didn't release a lock, you can very easily get a deadlock. No one else can traverse down the list anymore, and it's over. Also, if you acquire locks in the wrong order, you could easily end up in a deadlock. I need their lock, they need my lock. Right? Now you have a circular dependency, and it's over. So for the hand-over-hand locking, just to be clear, you still have to free the nodes. So when you delete a node, you can't just forget about freeing it. And that's what makes the linked list kind of difficult. You might have a reader or anyone traversing the list, and they're at this node that you want to delete. And for whatever reason, they got put to sleep for a little while, or things slow down for a little while, and now you go and free it while they are looking at it. And free overwrites the contents of the node, because it keeps a free list inside of the node space. So that's one way that you can really break things. Whoever's traversing it, if they're not holding a lock, then they could. You might free the list or free the node while they are trying to traverse the node. But as long as they're holding a lock on every node that they're traversing, that's okay. So what you want to do is you acquire the first lock on the list, on the first node, and then before you release the first node, you acquire the next node, right? Lock on the next node, and then you acquire the next one, and so on. So you release, after you've acquired the next, you release the previous, and now you have a new current and next to you. You can kind of move on like that, and that way you're guaranteed that no one can go past you and end up trying to traverse a node that you are about to delete. Yeah.
Does that mean that your data structure, like where you put the locks, has to be outside the data structure that you're iterating over?
No, that's fine. You totally just stick a lock in in the node. That's totally fine.
So like for deleting it, then you have to unlock before you delete the node?
That's a good question. Right, so say we now, and you have to do this for hand-over-hand locking, say you have a lock in every node, a pthread spin lock T in every node. So you acquire the lock, and now you go to free the node. Is that okay? Now the lock will be acquired forever. Any thoughts? Let's think about it for a little bit. I should use clickers for this. I gotta learn how to use clickers. I was reviewing a colleague's lecture for some teaching award, and he was using clickers really well. It's Chris Kanish. I tried once and I failed. Gotta try it again. Anyway, you had a question, suggestion.
I could see it going both ways, because on one hand, if you free it, then nobody's ever going to be looking at that specific pthread spin lock T anymore. So it may be locked, but it doesn't exist and nobody's trying to access it.
Mm-hmm.
But on the other hand, whatever store that function is keeping of the locks now might have like a memory address that might be reused. So even though it's not the specific variable, I don't know how that's specifically implemented.
Yeah, so I guess you're right. It depends on how the lock is implemented. You could imagine that there exists some sort of global state about the locks other than the lock variable itself. Maybe they are part of some linked list somewhere. Maybe there's some operating system state for the lock. You could imagine for a mutex. There could be other sort of a global external state. But as long as the lock itself is self-contained, like there's no other and nothing depends on this lock other than function calls, like you may try to lock or unlock the lock. In that case, it's fine. The fact that a lock is locked, what does that really mean? It means this byte was set to 1. That's it. And if no one's going to try to read that byte again and pretend that it's a lock, it's totally safe. It would look nicer to unlock the lock first and then release the node. So let's see.
You have to free the mutex or the lock when you delete the node. So if someone else is waiting on that lock while you're trying to delete it, I don't think that works until you unlock it. I think it needs to be unlocked before you can delete the lock. Isn't that basically unlocked?
So you're holding the lock.
Yeah.
Right? There's no deleting a lock. There's free. So you return the memory to malloc. But there's no real deleting of it. To delete a node out of the list, you would change the next pointer of the previous node to point at the next node, right? So basically, to do a list delete, you traverse the list with hand-over-hand locking. So now, when we exit that traversal, it's kind of a for loop, then now we're holding for previous and current. Right? Current is the one we want to delete. So what do we need to do? Well, we had to set previous next equals current next, right? So now we've deleted it. So now the question is, what do we do to recover the memory? And you could either say unlock current lock, or you could, well, you probably need to do at least one of these two. You certainly want to say free current. If you don't do that, you have a memory leak, and that's not okay. The homework template at the moment doesn't have a test for this memory leak, and I'm going to have to introduce one. So there may be an update to the homework template in the test part that checks for memory leaks. But anyway, we have to free it. So the question is, Do we unlock it? It's certainly not okay to first free it and then unlock it. Right? Because free, the assumption is that now anyone can use that memory. And we can't start overwriting stuff in someone else's memory. That's not okay. All right. So we could either just free it, as we just discussed. That's probably okay. But it's a little ugly. Like, semantically, do you really want to be leaving locks lying around locked like that? That seems weird. It's better to unlock it. Actually, we don't actually know what the implementation looks like. And we'll see. Can't think of a case where we would strictly need to do it, but when we start looking at lock design, you'll see that the unlock can be important at least. All right, so what about this? Is this safe is the question, I think. So now you've unlocked the node. Can we then go and free it without holding the lock? We have a no. We have a yes. Okay. What do we think? Yes? We can free it safely.
Well, if you maintain the lock of the previous one, then you should.
Come on, you're revealing the answer. Yeah, that's exactly right. So there's no way to get to the current node except by traversing the previous node. And we're still holding the lock on the previous node. So it's fine. It's not entirely obvious, this whole thing. Okay, so when you're inserting, the situation is a little different, right? And when you're traversing the list just to do a find, the situation is a little different. But the delete is certainly the hardest one. So now you got a lot of help here. Okay. Right. So the problem, I think, and I haven't run this particular part of the homework myself to get some performance numbers, but one potential problem here with this design, as opposed to the big fat lock design, is that we're acquiring a whole lot of locks. Right? For every node traversal, we have to do an atomic operation to say this is locked. Right? And then we get to the next one. Now we have to unlock the previous one, and so on. And those aren't free. As we know, atomic operations are strictly ordered. There's coordination between cores to ensure that ordering. There's no reordering of operations within the core in the sense of the out of order execution. Right? So it's kind of painful. So where's the trade-off there? Like, why would we ever want to have this many locks instead of just the one lock? One lock is cheap to acquire. Let's see. Okay. Here it is. All right, so we went through the big fat lock and big fat reader-writer lock. Oh, that one's pretty nice. So under what conditions would it be good to have a lock per item? All right, let me give you a hint. If we're all readers, it isn't. Then there's no point. We shouldn't have any lock at all. Right? It's all readers. If it's mostly readers, probably isn't a good idea still, because the reader-writers lock is very good there. You have parallelism among all the readers, all going together, and then, yeah, the writers, we kind of have to do one at a time. So when would we want to have one lock per item then? If it's all writers, okay, yeah, we're getting somewhere, yeah. If it's all writers, then clearly it's a, well, at least we're not getting the benefit of the reader-writer lock. So why would it be better to have many locks like this instead of just one lock in the beginning? Oh yeah, in terms of the homework, when you use a big fat lock, stick it in your lock struct. It's not a global. It should be one per list, right? Not one per program. Anyway, so what's the point here? We have many writers. That seems to be sort of the use case, but when would we want to have more than one lock? Yeah.
You can have concurrent writes of different segments.
Yeah, exactly. So you actually get some writer concurrency here. Because with the hand-over-hand locking, it's not like we're holding all the locks of the whole list. That would be completely pointless. But we're only holding 1 or 2 locks at any given time, maybe 3. Right? For a little while, we're holding 3 before we release the previous one, right? But so those, we're kind of moving on down the list, and while we're doing that, someone else can start moving down the list after us. So we have concurrency not just between writers, but also between readers and writers. Everyone can go at the same time, with some limitations. Right? The main limitation is you can't pass. Right? There's no way to traverse. If someone holding the lock in front of you, there's no way to go past it. Right? So that's, I guess, one limitation. Of course, you can't access the same elements at the same time. Okay, so, but there's got to be a trade-off here. Because it's also expensive to use all these atomic operations. So under what condition would it make sense to use these many locks? And when do we want to have just the one? Yeah.
It might be better in a data structure like a hash table. Because when you do all those atomic operations, you got to iterate through the list, through the entire list. So if your list is 1,000,000 long, you got to do 1,000,000 lock unlocks. But a hash table, you know exactly which one you want.
Yeah, that's true. So a hash table is what they call embarrassingly parallel. It's really easy to just run independent threads. But in this case, we're stuck with a linked list. We're given the data structure. Maybe we need the ordering benefit of a linked list. I don't know why we're using a linked list. But at least it's really easy to discuss. Now we can look at trees in a little bit. Trees are much better than hash tables in many ways. And they need the same sort of design. It gets more complicated than a tree. But let's talk about the linked list for now. So for a linked list, under what conditions would we want to have more than one lock? Okay, let's put it the other way. Under what conditions do we not want to have more than one lock?
There's only one writer.
There's only one writer? Interesting, yeah. Then certainly a reader-writer lock would make more sense. You can't have, under the current design, we cannot have readers concurrent with the writer unless, well, we can't have readers concurrent with the writer at all, because the writer could be changing something while you are traversing a node. It seems like we should just have all these locks all the time. I think that probably there's a case for a single lock if the list is short. Right? There's some, so we have some concurrency benefit. The benefit only kicks in at least if you have more than 3 nodes. Right? Because for 3 nodes, we have to hold all 3 locks. At some point, we're like, I'm at the current, I'm holding the previous, and I'm grabbing the next. Right? Probably I have, well, maybe I've released the previous. Maybe it's just 2. Right? It's enough to hold 2 locks at any given time. So if the list is of length 2 on average, well then clearly it's a bad idea, because now I'm acquiring 2 locks instead of 1, and there's no parallelism. Right? And I think it extends a little further beyond that. These traversals will be faster if you don't have to bother with all these atomic operations. So maybe if the list is, I don't know, 10 long, let's say, might still be nice just with 1 lock. After that, at some point, you'll see, and I think we will see this in the plots, you'll see that as the list grows, the scalability benefit of having many locks really takes over. But there's some big constant, or maybe a small constant, I'm not sure, that suggests we should use a single lock for small lists. So this actually works out nicely in a hash table. If you have a hash table with linked lists hanging off of it, right? Because then ideally in a hash table you would want to have like one element per bucket. But sometimes you get a couple, or maybe a few more, right? So in that case, probably would make sense to have one lock per bucket, but not one lock per element in the linked list hanging off of it, because we know it's going to be a short list. Right. Okay, so I guess the point there is locks are expensive, but the more locks you have, you get more concurrency. So there's always a trade-off, and be careful when you're deciding how to design your concurrency or your data structure. Okay, so still kind of problematic. I think we can do better. The problem here is that reading can't happen happen concurrently with all the writing, right? So we're most of the work really is reading too. Like, what do you do in a linked list? You run down the list for a long time, and then you make like one pointer change, and that's it. So it's not like the writers are doing a lot of writing work. So if we could somehow get the reading part to work without any locks, then we'd be in really good shape for a linked list, right? So we could somehow say, oh, I only acquire my locks when I make a change, and the readers don't use any locks. So what happens? Let's see. What are some? Okay. What if readers don't use locks? So what does a traversal look like? I guess it's I can even type it out properly. Right. There may be a condition. We're checking for some key. Let's try that too. If right. So really, what could go wrong here, right? So let's just do it without the locks.
Your writer or your delete could be in the middle of an operation, and you have a temporary break in the linked list.
How do you get a temporary break? Here's the delete, right? That's the one that does an X. Right? One single assignment. It's either pointers are atomically, or all writes, at least up to 64 bits, are atomic, meaning that you get the entire 64 bits in one fell swoop. It's not like you get like 3 of the bytes from the old value and 5 of the new value. So you get all the new pointer. The pointer will always be valid. I mentioned it before, maybe that's confusing things a little bit. This is actually okay, but it could be that the reader is not at previous, reading the next pointer, it's at current, right? It's at our current, which we're now freeing. And there's no guarantees, in user space at least, there's no guarantees about the timing here. So you could stop here. That's not right. Current equals current next, of course. Right. So you might stop here for a while, 10 milliseconds, while others are doing whatever they want, and then we're reading our current next pointer. How could we end up stopping for 10 milliseconds? Asleep? No one's trying to sleep. What's that?
Next is locked.
There's no locks. We're not using locks.
We finished our quantum of execution.
Exactly. Yeah. So you had it, but we finished our quantum of execution time, right? The OS decided it's time for someone else to use the CPU. That's one. So that's based on a timer interrupt, which happens periodically. There's other reasons too. Maybe someone hit a key. Hit a key on your keyboard, creates an interrupt. Maybe your CPU, the CPU this process happened to be running on, or this thread happened to be running on, is responsible for the keyboard interrupt, and so it gets interrupted. And then who knows what happens, right? All sorts of interrupts can stop the execution. Okay, so, but that's sort of general for any concurrent program. You don't know anything about the timing of the exact sort of interleaving of operations. It can get really bizarre. It can be millions of operations between here and here, right? And so, so what are we doing here? Well, current is still fine, so this should be okay. But then we go around. I mean, current, this is a local value. It's just a pointer. And we'll be okay unless we free somehow another thread in the process, free the memory that current is pointing at, and gave it back to the OS. We're fine. So we're checking the key. There may be garbage in there, so we probably didn't get it. But then we go around, and now we're going to current next. Okay, that's fine. At the next point, this could be a 0 now. So after that, we're trying to traverse from 0, dereference the 0 pointer, and then that's a null dereference. And now the process dies. Right? Okay. So what could cause this problem? The problem isn't free. So we get in here, we wait for a long time. In the meantime, someone goes and frees this node. And what does that mean? It goes back to malloc. And malloc will overwrite some of the values. Maybe that's not so important. Then some other thread asks for memory. They get this node. They insert it somewhere else in the list, right, with its own values in it. So now it actually gets worse, because now we were at a previous, we thought we were over here in the list. Some other node took the free, other thread took the free node and inserted it in the beginning of the list. So now we're suddenly traversing from the beginning of the list, right? Starting over again. Weird things can happen. Okay, so that's not okay. The readers have to use locks. Or is there anything else we can do?
When we have a big lock for readers and more granular locks for writers, and the writer has to get both locks.
Okay, so the suggestion is one big lock for readers and many locks for writers. I don't know how this would help. Oh, I see. Yeah, so it becomes a little bit like a reader-writer lock then, I think. But you would allow multiple writers. Now I see what you mean. So we would have a lock that says there can either be readers or there can be writers in the data structure. And with all these extra locks inside of the list, you can get concurrency between the writers, but the readers are locked out.
Yeah.
And then, yeah. So I think that's probably, under some conditions, helpful, at least if you have many threads. Right? If you only have a few threads, you still don't get enough concurrency to be worth all the trouble, probably. But if you have many threads or a really long list, yeah. Okay. But we can do better. I want our reader to not use locks. And we can do it. Yeah.
What if you make your writers wait? So, like a writer call waits to write, and then every so often, like your store buffer, and then it clears your writers into the list, and then you're
okay. Yeah, this sounds a little bit like what he's suggesting, but I guess you're saying readers and writers kind of traverse the list concurrently, and then the writers can sit there and say, okay, that's what I want to do, right? And at some point they get the clear to go, and then they write it in.
Mm-hmm.
Yeah.
Or maybe wait at the head of the list until the readers like one global reader's lock only allows readers.
But that's what he was saying, I think. Yeah. Yeah, but I think the key here for a linked list is that even the update operations do almost only reading. They're doing all these pointer traversals, and every pointer traversal is expensive. It's all data dependent, oftentimes in a multi-threaded case with updates. The cache lines won't even be in your cache, so you have to get it from somewhere else. And yeah, it's a pain. So you really want all that traversal to be in parallel. Yeah.
We have a reference feed from each node and we will indicate how many windows or items to find. Only when it is 0, we can provide an update.
Ah, okay. So we use a reference counter in each node to say how many nodes are looking at it at the moment, basically. How many has a reference to it. And only when it's 0 do we change it. Okay. Any thoughts about that? In fact, yeah.
Do you need locks for that reference counter?
Will you need locks for the reference counter? It's not that you need locks to update it, but you do need locks if you want to perform any operation dependent on the value. Any other operation than incrementing it. Increment and decrement, they're atomic operations for it. But in this case, we want to do a list delete depending on the value. To do that kind of operation atomic, we have to acquire a lock, check the count, and then delete the node. And now we're back to square one. And we're slightly worse off because we were managing the count too. So how did we end up with this problem? Right. Well, let me put it this way. That's the reader. We're not changing it. Maybe we make small changes on the side, but the reader traversal at least. That's it. So what can we do then? Yeah.
Could we move the node that we're going to delete to the end of the list before actually deleting it?
Move it to the what?
To the end of the list before actually
To the end of the list. Okay. How does that help us? Let's see. Before deleting it. So this is the deleting operation, at least in my mind. When we do that, it's no longer in the list. And so you would like to put it at the end of the list?
Yeah, I was thinking that if it sees it's at the end of the list and it actually is at the end of the list, then
Oh, okay. Well, I mean, I think you're almost there. We're pretty close here. But we gotta delete it. There's no choice here. We gotta delete it. I mean, that's the delete operation. We could delay it, like you say. I think that's a pretty cool idea. But the question is, how would you synchronize that? How would you know that no one currently is looking at this? Right. So you could try to say like, oh yeah, now we have enough writers waiting to do their work. So let's stop all the readers and then wait until the readers aren't in the list anymore. It's not very concurrent. There's really a lot of overhead there, so we can do better. So the reason that we can't do the traversal here so far without a lock is this. All right? It's not that this is a problem. We can traverse while this is being done totally safe. Right? We don't even need to execute the unlock, it seems. But in any case, there's no, the readers aren't using the lock, so who cares? So what if we drop the free? Now what? Is it safe?
If you point its pointer to the front of the list, it will, because then your reader will just duplicate some of its original code.
Oh, okay. So this is a sort of a maybe it's a consistency question. Like, is it what do we expect? And what does the reader expect to see? Right? So we should take that. We should bring that up again. Like, which value does the reader expect to observe when a writer has been writing? Right? That's a very important concern. But I'm currently more worried about the list just breaking or the program crashing. So we know that this one is okay. Right? Anyone that observes this previous node either gets what this value used to be, or they get the new value and they miss the one that we're trying to delete. And so they saw an old version of the list, or they saw the new version of the list that doesn't have the element in it. But the pointer that we're getting here is always a good pointer. So that means the traversal is safe, it's not going to crash. And of course, we're only interested in readers here, or say the traversal part of the update operations, and that's all they do. Okay, so what's wrong with it? Actually, let's discuss this value, which value you would expect to get. So clearly, there will be some cases where we are deleting the node while a reader is looking at that node. So the node is no longer in the list. It's still okay, it's a fine node, and it points correctly to the next element in the list. But in some sense, it wasn't in the list. Is that okay? Oh, depends on what the problem is, what the application is. I say no. Anyone else? Yeah.
We have a visible field which will be set to 1, and then this pointer will be deleted.
A disabled field, though, is that the one? Well, then the problem is probably the same. Like, this reader doesn't know if that field was set to disabled or not. It would have to.
If it finds a match, then it checks for a visible field. If it is not set to 1, then it says on that field, that particular node.
Right, but you still have the same problem. Because then after you've broken out of here, now suddenly the node is disabled. Like, you just missed it. So it's the same problem with the atomic. It's not atomic, your operation. But I'm saying this is correct. But there's one problem, of course. It's that we're not freeing the memory. That's no good. But
You're not guaranteed that the pointer, just because it was the current, you're not guaranteed that the next node wasn't necessarily deleted either. So you may say you deleted 2 nodes in a row. If you keep your current and then you follow the pointer to current, whatever your reader's looking at will think that it's in the valid list, but it's really in this delete space.
I agree, but it doesn't matter. So my current node was deleted. Right? It's pointing to this next node that was also deleted. And I keep going along this, I get really unlucky. So I keep going along deleted nodes. And at some point I pop up into the normal list. And I'm saying that's okay. Okay, now let's see. I think I will stop this recording. Okay, let me just save that too. Sorry about that. Okay, so just to reiterate, what happens here is it looks like the reader is reading a value from a node that's no longer in the list, and that shouldn't be okay. But in practice, the result is exactly the same as if the reader just read this node a little bit before the writer came in. And there's no way to tell which order they actually executed anyway. Or at least there's no guarantee about which order they would execute. So in the end, the list performs the exact same thing it would with locks in place. Like with locks in place, the reader might get in before or get in after. So it's similar to what we're saying about reads, right? That reads can get reordered by the CPU. You get stale values. This was a somewhat stale value. That's okay. On the other hand, if you're an application developer and you're using this list and you really care about the order, right? Say that you have a producer and a consumer, and the producer has told the consumer that something ended up in the list, and the consumer expects it to get it from the list. All right. So now you have this happens before age, we talked about before. There's that communication between the producer to the consumer. In that case, the happens before edge actually guarantees it. So in that case, the producer does the work, puts it in the list, sends a message using an atomic operation to the reader, and then the reader goes and reads it. So now there's an actual ordering provided. So then you'll be okay. Of course, that's a lot slower than both of them just blowing through the list asynchronously. Right, so there's something missing now. All right, this is not okay. We can't just not free it. So what are we going to do? Yeah.
Implement some sort of garbage collecting operation.
Implement some sort of garbage collecting. Yeah, this is exactly right. A little vague, perhaps, but so if you were doing this in, say, Java, you just do it like this. That's fine. Because the Java garbage collector will at some point discover that here in the heap, so the way the a garbage collector works, does anyone know? No? Okay, so, well, you know, good.
Yes. We created one last semester.
Oh, in 361?
Yes.
Awesome, I designed that one. Good, they should be.
It traverses the list, or it traverses all the static references looking for references to the heap, and it doesn't find any. It knows that there's no references on the stack to
Yeah, and from globals and so on. The basic idea of garbage collection, at least, is that we have a list of objects on the heap. That's basically what malloc does anyway. You have all these chunks. If it's in Java, it'll be some other list of all nude objects, like NEW, right? NEW. So whenever you make a new object, it ends up in this list, one way or another. And then if an object doesn't have a pointer to it anymore, eventually another thread will go and free that memory. So how do you know if there's a pointer to it? Well, in this homework in 361, it was kind of a little bogus. Any value that looks like it might be a pointer has the same value as the address of the object you're interested in. We call that a pointer. So we just traverse all of memory and see, are there any pointers to this one, any kind of pseudo pointers? And if not, then we get rid of it. How you do that traversal, it depends on the language and so on. But the point is, with a general purpose garbage collector, you can just remove your pointer to the object, and the object eventually disappears when there are no other pointers to the object. In this case, there is a pointer to the object, right, sitting on the stack. And so the garbage collector would know that and not collect the object until we've gone one more time around. Now there's no reference to the object anymore. But we are doing this in C, and there's no garbage collector. And don't use the garbage collector from 361. That was more of a fun homework.
just create a list of 3 nodes, and then every so often traverse the 3 nodes.
Excellent. Okay, so let's say free list next. Oh, let's see. We do current next equals free list. let's see. No, free list equals current. There it is. Right? So we've added it to a free list. Very good. Now we know at least that it needs to be freed. We don't need to worry about the garbage collector anymore because we have a list of, maybe it should be called a to be freed list, really. Right? We don't need to worry about the garbage collector. We can just every so often run through this to be free list and free everything in the list. What does this every so often mean, though? And who's actually running through this list?
Another thread.
Another thread, yeah, okay.
And every so often there should be enough time to be sure that the thread, the reader has executed and went to the.
Yeah, okay. So we're saying we have another thread, like an extra thread, I guess, that, say, sleeps for a while and then frees it. And the while should be long enough that anyone that was using these elements no longer is using them. Doesn't seem quite right, though, because we could be adding things to this to be free list at any given time. So there could be something really fresh in there.
But couldn't we just remove the extra thread and the writer waits enough time before doing the free?
Ooh. Okay. Okay. So, all right. So here's one option. Let's see. Another option. Sleep some time and then free. Okay. Let's see. I guess there's a couple of problems here. How long should some time be?
Do we have any form of guarantees?
Nope. Well, no. If the machine is really busy, you're not going to get the CPU back after 10 milliseconds. If you have 1,000 processes on the same CPU, it'll take you 10 seconds or more, 100 seconds. We probably don't want our writer to be sleeping for 100 seconds. Of course, most of the time it would work. But that's not what we're going for. Yeah, there's two problems with it. One is how long should we sleep, and it's undefined. The other one is we have to sleep. It'd be much better if the writer could do some other work. Yeah.
You have a big fat lock that's just for the free.
Ooh, a big fat lock just for the free operation. Okay, let me delete this other option here because that one it's a little too dangerous. So we have a lock around this one. How does the lock help the readers?
It prevents readers from getting there as well. It just completely shuts down the data structure if the data collection operation is.
Oh, I see. So when you want to do the garbage collection, you lock not just the free list, but the entire data structure. And then you go and free the list. But the readers don't use a lock. Maybe we could use one of those writers locks. And so if you're just a no, that's not okay either. No. Any other ideas? Yeah. We free it after the reader's done. Okay. That's a great idea because when all the readers are when all the readers are done, right? It's not enough with one reader.
We count on all the reader, and after the reader comes to come to 0, then we count the free.
And then we kind of prevent the readers from coming in until we're done. Actually, that doesn't matter because new readers are okay. It's just if we know there are no readers in the list, then we can start freeing. And we know that all the new readers coming in while we're doing the freeing, they're not seeing all this stale stuff anyway. oh, maybe we should have two lists, right? One for the one that we're currently freeing, and one for the one that we're putting stuff into. Okay, well, I like this idea of, like, we can really only free this stuff when we know that there's no reader that wants to use it. Right? None of the nodes in here can be freed until there isn't a reader that has a reference to it. The question is, how do we know when that's happened? How do we know the readers are done with our objects? Yeah.
You could put like a barrier on the last item of the list. When all your readers hit it, you know how many readers you have.
Well, the readers aren't going to the end of the list. But you could put something here, like when they're done traversing, then we know that they're not going to do any more of these. That's the dangerous one. Probably that's okay. So what would we put over here then? It is tricky. It would be so great to have this concurrent readers and then just have a lock for writer. The design is called RCU, read, copy, update. And that's just this general idea of lock-free readers and locking writers. But all of RCU, every RCU design needs to deal with this problem of the garbage collection. So we can't free it until the readers are done. If you're doing it in an OS context, you're developing a kernel data structure, then you can actually provide guarantees. The OS is in charge. It knows that there will be, like, if my kernel code starts traversing this list, you can even guarantee that it will not be interrupted. Right? The OS can just cancel any interrupts for now, disable the interrupts, go through the list, and then re-enable the interrupts. So now we know how long it's going to take. Well, depends on how long the list is, I suppose. Actually, that's important too. If the list is really long, it could become a problem, potentially. No, it's really like, how long are you holding one of these? Yeah, so you can start providing some guarantees, and that's what they do in an OS context. You only use these RCU data structures when you know that operations, depending on, like, reader side operations, will finish within a certain amount of time. It's called an epoch, I think. It's not like the Unix epoch, which is at the timestamp. So what they do is they say, okay, we will globally guarantee that all the code within the kernel will not, like, touch this data structure or any element of this list for longer than 10 milliseconds. And then you just have two lists, right? One for the previous 10 milliseconds and one for the current 10 milliseconds. And then you switch them. Every 10 milliseconds you switch them and you free the old free list. And that's that. Because you know for sure that everything that's in the previous 10 milliseconds free list is not being used by anyone, because you guaranteed it throughout your code. So that's one way to do it. But we can't do it in user space. In user space, we don't have that kind of guarantees at all. So, what do we do instead? Yeah?
Can we use the atomic operations to maintain a reference?
You mean a reference count on each?
Yeah, like a table.
On each node. Yeah. So that's basically what Arjit proposed, where we would. That's fine to do a reference count with atomic operations. Of course, it's really expensive because now it's basically like acquiring a lock on every node. But then the problem is the writer needs to know, like, while it's doing the work, it needs to know that that doesn't change. So an atomic operation just to increment it isn't enough. It needs to lock the node, lock that count. So it doesn't work. Okay, so here's the idea. the readers will say something, right? So when you're done, it's called a quiescent period. That's what it is in the kernel. It's a quiescent period. It is not an epoch. Right? It means things will be quiet after this long. Right? You're not going to be touching these things after this long. Quiescent period in this case is a function call. I am done. All right? Okay, so now the reader says, runs this function, I'm done, and if there are no other readers, we need something more. All right. I am starting. Okay, so this is starting to get pretty good. So you acquire, well, you don't acquire anything, you say starting, and then at the end, say I'm done, and if everyone's done, there are no readers in there, then we can free the free list. But there probably will be readers in there. If we have enough threads, there's always going to be someone in there, so we'll never free the list. It's not quite right. How can we fix it? It's almost done. Yeah.
We have some versioning or timestamp.
Timestamp. That's right. So let's call it a version. And on here, or on any modifying operation, we increment this version. That's an atomic increment. When you make a modification to the list, you increment the version. So now at least we have like a monotonically increasing version count for the list. And then when you start reading, you know what was the version when you started. So anything that you're getting in here will be that version or later. Right? Maybe the list will change while you're working on it, but it's not going to get older. Right? So that's fine. So now you say, okay, I'm done with this version. And take the min of all the readers. As long as there isn't a reader that is older than, okay, so let me back up. You have this node. It used to be in version number 5. The node belonged to version number 5. We deleted it from version 5. We made version 6. There's a bunch of readers. They entered at version 3. Right? Eventually they leave. They're done with version 3, doesn't help. Some more readers come in, they go out. There are no readers left that are any older than version 6, any lower number than version 6. In that case, we know that there's no reader that wants version 5 anymore. There's no reader touching this element anymore, right? So it's safe to free it. So now you could, in principle, you could have a sorted list, a sorted free list, right? And you keep track of what is the oldest reader. And whenever the reader says it's done, it frees up any element that's older than that reader. Because we know that those are safe to delete. Sorted list is kind of expensive. So you don't do that. Keep a set of buckets. So we say just, any version from 0 to 100, 100 to 200, 200 to 300, right? Some sort of thing like that. And you just get a little less aggressive with the deleting. So you say, okay, I'm version 200. Anything that's version 100 and below is fine. So you delete that. Sound good? So this is called Q, I don't know. The design was called QBSR or something. I don't know. This is how you basically have to do this RCU read copy update in user space. So we don't have guarantees about the time, but because every reader says which version it was working on, we know when stuff is, when some of our nodes are ready to be freed. So I guess there's one more thing happening here. When you say I'm starting, there has to be some sort of accounting saying, oh yeah, I had a reader entering at this at this version, right? So we could keep another little linked list, I suppose, of readers. And then when we say I'm done, we check that list of readers to see if we're the minimum. If we have the oldest version, that means we're responsible for freeing a bunch of elements. So in the next homework, we'll use an existing library for this sort of RCU stuff. Designing it is also cool, but maybe a little bit too much for a 1 week homework. All right, still a problem though. I mean, this is awesome. It's so much better than what we had before, because we're traversing this list without any links. Without any locks, and of course, all the work we're doing in a linked list is all this traversal. You can do something similar for a tree. Trees don't have as many traversals. It's only log n traversals. It's better, but you still need to worry about this concurrency. Like the top of the tree, every time you want to go through the tree, you have to start at the top. You want to have a lock at the top. That's basically a global lock here. That's terrible. So it's much better if you can just blow through it. If you're a reader, you can just traverse through it without any locks. Same thing applies, but it gets more complicated, and that will also be part of the next homework, I think, probably. What happens when you forget about balancing trees, but just when you delete a node, it's not exactly the same. Sometimes the tree structure has to change when you delete a node a little bit. 2 places at the same time. But anyway. The linked list still has a problem, and that is that the writers don't get to operate concurrently. Right? They have to acquire a lock. Well, okay. It's very concurrent. It's not completely concurrent, but they, in order to make a change, the traversal is now lock-free. But then they have to acquire the locks on the previous and the current before they do anything. And that's not always ideal. Acquiring a couple locks here, we can do better. So ideally, we would just want to kind of do the work without locking. Right? That's much better. So we, instead of acquiring the previous and then acquiring the current and then doing all this stuff, right? We just, for delete, we just set it to this. Forget the lock, we just set it. What do you think? What could happen if we try to delete now? It's different with insert, but say we just try to delete this here and we don't acquire a lock. What's the worst that could happen?
Point at the node that you already put in your delete list. So.
So someone else deleted next.
Or somebody's on. I guess somebody else could have already.
Concurrent next point to install.
How would that end up? How would we end up in that situation? I think there are many things that could go wrong, but let me propose one. Say that someone at the same time inserted an element between previous and current. Right? So now next has updated to include another element, but suddenly we're getting there and overwriting it. So that essentially means we deleted that previous element, but there was the user didn't say delete that element. That was just a mistake. So that's not okay. It's not an ordering thing. It just disappeared, and we didn't free it. So that's the problem here. We can't really have two writers operating at the same time. Lock is good, then it works just fine, but it's kind of inefficient. So it depends a little bit. In this case, maybe I'm kind of struggling to justify the next design, but let's do it anyway. So if we don't want to have a lock, oh, here's a good one. Anything that deals with locks can end up in a deadlock. Right. You have some poor software engineering, let's say. You could end up with a deadlock. Or you could have, this is a really good one, not a deadlock, but say another thread grabs the lock and then gets put to sleep. And now here comes my critical priority thread that is about to start the rocket or whatever. And it needs to acquire this lock. Right? But the other thread is holding the lock and it's asleep. So now my rocket doesn't start, right? Until the first thread wakes up. So this is called a priority inversion problem. You have a low priority thread that runs through the list, acquires a lock, it's fine, and then, okay, high priority thread comes in and needs to do something, right? So low priority thread goes to sleep, holding the lock still. And now the high priority thread blocks. This stinks. There's some other solutions to it. Like you could try to do, like, give this low priority thread higher priority now because someone is waiting for it. There's OS solutions for it, but a much better idea is to just not use locks, right? Because then there's no blocking, and that's great. Okay, so that brings us to a lock-free design. So let's see. So it used to be like this. To delete, the reversal was already lock-free, so that's fine. I think for the free list, we can make it lock-free too, but let's not worry about the free list for now. Just this thing. We have what it takes to make this safe. We've discussed some primitive that makes this assignment safe. We use it when we implement locks. So it goes like this. If compare and swap. Old, previous, next. Oh, maybe we say like this. While not. Actually, that's ugly too. Let's go like this. Okay, so this compare and swap, right? It's exactly what we use for lock implementations. We're not implementing a lock here, we just try it once. So we say, oh, I'm trying to insert my current next here. And that's fine, as long as the previous next hasn't changed yet. So before we start preparing the current next for insertion, we keep this old value of what it used to be. This pointer used to look like. And then we say, oh, if it still looks the same, then just insert my element. Right? Then we make this assignment. If it doesn't look the same, well, then we're going to have to try again. Right? So here, actually, there's no if. It's more like an if not, abort, and retry. So this one, actually, is this clear? Anyone need any further explanation of the compare and swap part? Okay, maybe that's somewhat obvious. Why is it safe? Well, if it's still the same pointer, it hasn't changed. Like the whole list before it could have changed, but we're just trying to add something or delete something in this case between the previous next and the current next. That's all we're trying to do here. So within that those small confines, this next pointer indicates if anything's changed. Okay, so if it had changed, then what? what does it mean, abort and retry? It means we have to start from the beginning. Right? So now we have to traverse the list again. We don't know that we are anywhere near a safe node anymore. Someone changed the node just before us. This is weird. So we stop whatever we were doing and then start from the top of the function, try to find the right place to insert, or the right place to delete, I guess, in this case, and then do it again. So what do we think? Good idea?
It seems like almost you couldn't guarantee that certain things would happen. Like, it seems like you could be stuck infinitely searching through if you got really unlucky.
Yeah, agreed, yeah. So you could end up in a situation where someone keeps changing this previous next on you. Every time you make it there, you want to delete your node, someone else has changed the next pointer over and over. It's a little problematic, but you'd have to be really unlucky. I guess you could probably imagine a live lock sort of situation where you have two nodes kind of fighting over the list this way. I would think that at least the other node made progress. The other thread made progress. Someone's making progress here. It's not really a lock. Probably it's not going to keep doing it forever. Probably you're okay. Another potential problem here is that if you have a lot of these conflicts, you end up doing a lot more work, right? With locks, yeah, okay, it's kind of expensive to acquire the lock. You have the potential problem in really performance critical operations, not performance, but in latency critical operations. This is awesome. I mean, if you're doing any sort of operations with a cyber physical system, you're steering a car or trying to, you're stopping the X-ray machine or these sort of things. You don't want timing to affect your lock acquisition. So here that's really great. But whenever there's a conflict, you can potentially have a high cost of recovering from this failed compare swap. So it's high in the sense that you have to do all the work again, and maybe again. But that's oftentimes worth the price. Okay, so there's actually a bunch of other ways we can do this, but we're out of time. And next time, I think we'll talk about various other alternatives to synchronization for shared data structures. Thank you, and good luck with the homework.